Assalamu alaikum. So let's solve the first exam, and I will start with question number 1. We're given a signal flow graph with a closed loop transfer function. We need to find certain unknowns alpha 1 to alpha 5. So the first thing, I need to find the closed loop transfer function from the signal flow graph. So I need to find y over r, which according to the Mason-Gain formula will equal the summation of I equal to 1 up to n pi delta I over delta. So we need to find the first thing, the determinant, which depends on the loops. So we'll start with the loops. So here I will write the loops gain. And let's assume that I'm starting with node number 1 here, and this is node number 2, this is the node number 3, and so on, until I'm having node number 8. So if I check node number 1, 2 branches out, so impossible to have any loop here. Let's go to node number 2. I will have one loop. So this is the L1. Now the loop gain of L1 will equal to beta G, and this is for node 2 and 3. No more loops. Let's go for checking node number 3. We have this loop, so this will be L2, which has a gain of 1, 2, 3, 4, 5, so G to the power 5, which pass through 3, 7, 6, 5, and 4. No more loops. Let's go to node number 4. I'm having the following loop, so this will be L3. So here L3 will equal to beta, which only associated with node number 4. Node number 5, the same L2. Node number 6, I'm having the following loop, which is the L4, and L4 here will equal to beta G. Node 6 and 7, and finally we have the following node, which is the L5, and this will be beta G, which pass through 7 and 8 node. If we examine the signal flow graph, we can see that L1 does not touch L3, does not touch L4. So here we have 3 non-touching, which is L1, L3, L4 are non-touching. Also, if we check the signal flow graph, we can see also L1, L3, L5 are non-touching. So we have another combination of 3 non-touching, which is the L1, L3, L5 are non-touching. So if we have a 3 non-touching, this means that we have 2 non-touchings. So here the all possible combination of the 2 non-touching will be L1, L3, L1, L4, and L3, L4. Also here, from this combination of 3 non-touching, we have the L3, L5, and L1, L5. I'm not writing L1, L3 because already I have it here. So after specifying the loops, gains, and deciding the touching and the non-touching loops, we can write the determinant delta will equal 1 minus the summation of all loops. So it will be L1 plus L2 plus L3 plus L4 plus L5, then plus the product of the combination of 2 non-touching, which are here. So those will be L1 L3 plus L1 L4 plus L3 L4 plus L3 L5 plus L1 L5. Finally, minus the all possible combination of 3 non-touching. Here we have the 2 combination, so it will be L1 L3 L4 plus L1 L3 L5. So now we can substitute the loops again inside the determinant and find the determinant. Now if we do so, we can write the determinant as delta will equal to 1 minus 3 beta g plus beta plus g to the power 5. Then for the 2 non-touching, if we collect the terms, this will be 3 beta square g plus 2 beta square g square. For the 3 non-touching, we have 2 beta cube g square. If we rearrange it, we will have the delta will equal to minus d to the power 5 plus 2 beta square minus 2 beta cube g square plus 3 beta square minus 3 beta g plus 1 minus beta. Then we need to specify the paths and the cofactor. So simply we can stand on the input, we can look toward the output and ask ourselves how many ways, how many paths we can go from the input to the output. If we examine the signal flow graph, the first path will be this one. So simply here P1, the gain for that will be G multiplied by G multiplied by G multiplied by G multiplied by G, so G to the power 5. And this path touch everything except L3, so the cofactor for that will equal delta, such that all the loops except L3 equal to 0, so I will end up with 1 minus L3. So L3 is equal to beta, so this will be 1 minus beta. Again, if we check the signal flow graph, we can have another path. This is the another path. So here we have the P2, which will equal G to the power 4. The determinant for that will equal, now P2 touch all the loops except L1 and L3, so this will equal 1 minus L1 plus L3 plus L1 L3, which means that I can go to the determinant and put all the loops except L1 L3 equal to 0. So let's write the P1, this will equal G to the power 5, and delta 1 was equal 1 minus beta. P2 is equal G to the power 4, and delta 2 will equal to 1 minus beta G plus beta plus beta square G. So now we can write the closed loop transfer function, which will equal T of S equal Y of S over R of S, and this is equal to P1 delta 1 plus B2 delta 2 over delta. So we have everything here. We have delta, we have P1, and we have P2, we have delta 1, and we have delta 2. So this will equal P1 is g to the power 5 multiply 1 minus beta. P2 is plus g to the power 4 multiplied by 1 minus beta g plus beta square g over the determinant delta. If we rearrange it and write it, this will equal to, if we collect the terms, we will have the 1 minus 2 beta plus beta square g to the power 5 plus 1 minus beta g to the power 4 over the determinant, which was minus g to the power 5 plus 2 beta square minus 2 beta cube g to the power 2 plus 3 beta square minus 3 beta g plus 1 minus beta. This must equal to the given transfer function, which was alpha 1 g to the power 5 plus alpha 2 g to the power 4 over g to the power 5 plus alpha 3 g to the power 2 plus alpha 4 g plus alpha 5. Now, in order to compare, we must match the gain here with the gain here. Here is positive, here is negative, so this means that I need to multiply by minus 1 here and minus 1 here. So if we multiply, we are getting now y over r in terms of beta, and g is equal to 2 beta minus beta square minus 1 multiplied by g to the power 5 plus beta minus 1 g to the power 4 over g to the power 5 plus 2 beta cube minus 2 beta square g to the power 2 plus 3 beta minus 3 beta square g plus beta minus 1. So now we can compare. If we compare, we can get that alpha 1 is equal this equation, alpha 2 is equal this equation, alpha 3 is equal this equation, alpha 4 is equal this equation, and finally alpha 3 is equal this one. So now we can write the values for the alpha in terms of the beta, so such that alpha 1 is equal to beta minus beta square minus 1, alpha 2 is beta minus 1, alpha 3 is 2 beta cube minus 2 beta square, and alpha 4 is equal 3 beta minus 3 beta square. Finally, alpha 5 is equal beta minus 1. So only you need to substitute the value of the beta to find alpha 1, alpha 2, alpha 3, alpha 4.